In the next section, we take a look at mechanisms of laser-induced damage and operative damage phenomena. As you can see, the laser-induced damage phenomena and by the type of damage includes bulk active, surface, nonlinear materials for thin films, and infrared components. So in the case of bulk active, particulate inclusion, self-focusing, electron avalanche are important. For surface damage, mostly electron avalanche. In the case of nonlinear materials, particular inclusion, self-focusing, and electron avalanche, as well as thermal, all type of damage phenomena become important. And in the case of thin film, which is what we're dealing with, particulate inclusions, electron avalanche, and thermal phenomena are key. And the rest is for infrared components, particular inclusions, and thermal. So we'll focus more on the thin films. So in the next slide we see a rule of thumb for laser-induced damage after Soleil, which is the energy damage threshold fluence in joules per centimeter squared, and the laser pulse width in seconds, TP, are related by the equation 15.1. So that would imply, for example, for a 195 microsecond pulse of a laser, you would require approximately 4.416 kilojoules per centimeter squared for laser-induced damage. In the next slide, we'll take a look at the effects of rubidium inclusions in the thin film. From glass and otsu, particulate inclusion plays a major role in laser damage, especially for metallic inclusions such as rubidium, due to the presence of free electrons. As you can see from equation 15.3, the delta E, or calculated critical power and energy absorbed by the rubidium ion inclusion. For example, in table 19, we look at a 100 kilowatt per centimeter squared laser showing the effect of 1.95 10 to the minus 4 seconds of a pulse laser, and we could see the absorption coefficient at rubidium at 780 nanometers, approximately 0.97. The diameter of the rubidium ion is around 3.32 times 10 to the minus 10, and so we have a net energy change of 1.689 times 10 to the minus 7 joules. Now if that laser were on for a lot longer, say for example 1 second, and we plug the numbers in, we essentially get a delta in energy of 8.66 times 10 to the minus 4. And so the longer the laser will be on illuminating this thin film with the rubidium inclusion, the more energy delta E will be absorbed by the rubidium inclusion, producing local heating in the area around the crystal, producing deformations and affecting the microstructure of the thin film. In the next slide we'll discuss self-focusing, and in any transparent dielectric medium, the refractive index shows a weak dependence on the local intensity of the transmitted light related to the refractive index as n equal n sub 0 plus n sub 2 times the square of the local optical frequency electric field. And in calculating for 780 nanometer, show the speed of light, then pi 3.142, then the n sub 2 equal 3.0 times 10 to the minus 14. We can calculate a critical power, which self-focusing becomes important, of 19.2 megawatt at 780 nanometers. So for DPALs, self-focusing will not become an issue until somewhere around 19.2 megawatt. So next we will discuss surface damage effects in the thin film. Table 21 shows the ratio of laser exit intensity, that is the exit intensity after passing through the thin film versus its intensity on the entrance to the thin film. You can see the ratio is given as 4 times the refractive index of the material squared divided by the refractive index of the material n plus 1. And the assumption here is the laser will be going through air of index n equal 1 into the thin film material n, or refractive index n. So for silicon dioxide, you can see the refractive index 1.539 and a ratio of 1.469. For zirconium dioxide, it's and is 2.184. The ratio is 1.882. Tantalum pentoxide 1.786. The ratio is 1.644. Aluminum oxide, the index is 1.76. The ratio is 1.63. For titanium dioxide, the index is 2.489. The ratio is 2.036. And as you can see, titanium dioxide clearly has the highest ratio of laser exit intensity versus entrance, followed by zirconium dioxide, then by tantalum pentoxide, aluminum oxide, and then silicon dioxide. So the implications are, with regard to surface damage effects, is that the for laser-induced damage is that the damage phenomena would be more pronounced for silicon dioxide, and on the higher scale less pronounced for titanium dioxide and zirconium dioxide. Next we will discuss electron avalanche, a very important phenomena concerning thin film. And so essentially what happens is a laser-induced electron multiplication under high-intensity laser irradiation. And it's based on the density of free electrons in the conduction band after Shang, 2009. So while the high-power laser irradiates the optical material, the electron density in the conductive band increases quickly, then results in an alteration of the dielectric constants. When the electron density increases to critical electron density, then it makes a sudden change in dielectric constant. At this time, the refractive index will suddenly decrease, and the reflective index will increase rapidly, thus leading to a plasma spark and an advanced avalanche of the electrons. So the electron avalanche will lead to damage of the thin film.